Okay, it's a great pleasure to have Shang from Institute of Physics at Chinese Academy of Sciences as our speaker today. Shang is an expert on many topics, ranging from uh, molecular materials to generalized symmetries to quantum information, and maybe to also to non-Hermitian physics. Today, he's telling us about constructing bulk topological orders via layered gauging. Sean, please go ahead.
Thanks, Liu Jun, for the invitation and for the very nice introduction. The title of my talk today is Constructing Bulk Topological Orders via Layered Gauging. And this talk is based on this paper posted earlier this year. I suppose you can see my cursor. Uh, so this talk is closely related to a concept known as topological holography, which is a framework or a principle that says that given any k-dimensional generalized symmetry, there exists a k plus one dimensional topological order, which can characterize the topological features of this symmetry. And the physical realization of this holography principle is just by the bulk boundary correspondence of the topological order. And this framework or this principle has been found to be very useful for understanding quantum many-body states with generalized symmetries. For example, in 1+1 dimensions, one can ask the following question. So suppose I consider 1+1D system with the Z2 Krummers-Wannier duality as a symmetry, then what are the possible gap faces allowed by this symmetry? And using this holographic principle, we can show that there's actually only one gap face with this symmetry. And this gap face is also very interesting and has threefold Gaussian degeneracy, spontaneously breaking this Z2 Krummers-Wannier duality symmetry. Using this framework, we can also obtain some useful information about quantum critical points. Again, for example, in 1+1D, these orders shown by this kind of holographic arguments that all unitary minimal models, which is the infinite class of the formal field theories in 1+1 dimensions, they all have they have no anomalous symmetries. Okay. By the way, and you can uh, feel free to interrupt me at any time and ask questions.
Sean, I already have a question. In
Sure.
example two, but here in example two, when you say symmetry, do you mean ordinary symmetry or any symmetry?
Um, I guess ordinary zero form symmetry. But in 1+1D, there aren't many other. Um, of course, the Krummers-Wannier duality symmetry should be excluded, I think. So it should be ordinary zero form symmetries.
Okay.
Yeah. So what they did is that they first classify what are the zero form symmetries in those minimal models and whether they are anomalous or not. The answer is they are all anomaly free.
Okay.
Yeah. And I think yeah, it's a good question. I think this only zero form symmetries is included. Or zero form invertible symmetries are included in this thing. Okay. So since this framework is useful, a natural question is that given a k-dimensional generalized symmetry, how can we identify the k plus one dimensional topological order that hosts the symmetry on its boundary? And people already have many frameworks that people already have many well-established examples. For example, in given any 1+1 dimensional fusion category symmetry, uh, there's a well-known 2+1 level one string net models. This is a Hamiltonian model. There's also a C-sum TQFT correspondence, which is the Turayeviro TQFTs. Yeah, and these are the 2+1 topological orders which host this future category symmetry on the boundary. Also, given any zero form symmetry G, any discrete symmetry G in any space-time dimension K, there's a K plus one dimensional digraph written T2FT, which corresponds to this symmetry. Okay. Uh, and in fact, this type of construction is quite general. According to this comment by Kevin Walker on math overflow, basically given any n category with the right sort of properties, there's a standard way of constructing an n plus one dimensional TQFT that has this symmetry on its boundary. I don't know whether this is published anywhere, but Walker is expert on this type of thing. So I suppose this is something standard to the experts. A common feature of all of these constructions listed here is that they rely on a higher category theory, which at least to me is a rather heavy mathematical framework. And a shortcoming of all of these category-based constructions is that they are not applicable to subsystem symmetry. And this is because the bulk theory corresponding to subsystem symmetry is very likely to be fractal topological orders. And so far we don't have a very good mathematical understanding of, we don't have a very good mathematical description of fractal topological orders. Okay, and this motivates the work, the result, the work in what we did in this work. So here, I propose a new method that can produce a k plus one dimensional lattice topological order from a k dimensional lattice symmetry. This method, this is called the layered gating method, and this method is purely based on lattice symmetry. It doesn't require any categorical description of the symmetry, and therefore it is somewhat more versatile. For example, it can be applied to the case of subsystem symmetry and can produce fractal topological orders. I should say that this paper is not the first work that can do this sort of thing, and I will comment on relations to other papers near the end of this talk. Okay. Is there any questions so far about the setup and what I'm going to do here?
Sorry, I have a question here. So
Uh-huh.
you just mentioned the topological holography. I just wonder, what is the precise relation of the boundary symmetry and the bulk topological order, or more precisely, like given the boundary generalized symmetry or just zero form symmetry, you should specify its symmetry group and maybe symmetry action. And
Sure.
how does this data correspond exactly to the bulk data?
Sorry. That is actually the question we wanted to understand here. In the case where the symmetries can have has a categorical description, people already have very well established way of describing the bulk topological order. There's some functor in category theory that can do this job. And more physically, what happened is basically as follows. When you have some k plus one dimensional topological order in a bulk, say like in a disk region, some symmetry will be enforced on the boundary of this topological order, and that is roughly so the symmetry being enforced by this bulk topological order is the symmetry corresponding to this topological order. This is a less rigorous but more physical description. Does this answer your question?
I see. Thank you. Yeah.
Yeah.
Okay. Yeah.
There's a more systematic description known as a sandwich construction. I didn't describe it here because I want to use it in the rest of the talk. But there's a somewhat more the picture I draw here is the simplest picture, but there's a somewhat more precise description where you have a topological order on with two open boundaries, and you can specify some you have a topological order you have a topological order in a k-dimensional system with two open boundaries, and when you take the quasi k-dimensional limit, that is when you take the thickness of the topological to be very thin, the system becomes a k-dimensional system with a corresponding symmetry. Yeah, there's a somewhat more concrete way of doing it, but I will not describe use it here in the rest of the talk. Okay. Okay. So as I just said, what I'm going to do in this work is that I'll introduce a method that can generate k plus one dimensional topological order described by a lattice Hamiltonian, given a k dimensional lattice symmetry. And in the rest of the talk, I will try to explain this construction using a few examples. Okay. I will first consider the simplest situation, that is the input symmetry is an invertible abelian and onside symmetry, which I call A. Onside means the symmetry is normally free, and invertible and abelian, okay. So later I'll generalize I'll generalize the symmetry to more sophisticated cases, but at the moment let me focus on this simple case situation.
Is the symmetry group discrete or continuous? Doesn't matter.
Discrete.
In this talk, will you talk about anything like the continuous symmetry?
No.
I see.
Only discrete symmetry. So our prescription is as follows. So as a first step, we stack a series of k-dimensional quantum systems. Each of them has the symmetry A into a k plus one dimensional pile. This is shown on the left-hand side of this picture. And then at this moment, these different layers are decoupled, and each of them has a symmetry A. And I will use this notation U sub n and A, U sub n comma alpha as the symmetry generators of the symmetry, where n is the layer index and alpha is the internal index labeling the different generators of the symmetry A. So for each given each given layer index, U sub n alpha generates a symmetry A acting on that particular layer. Okay. So the key step of the construction is that we want to sequentially gauge the bilayer symmetry generated by UN alpha times U inverse n plus one alpha. So this is a symmetry. This also generates a symmetry group A. Because I'm assuming abelian, so U and U inverse has the same multiplication rule. So this symmetry acts on two neighboring layers, and generates a bilayer symmetry A. So I want to sequentially gauge these bilayer symmetries, which means, for example, I can first gauge the symmetry, this type of symmetry acting on the first two layers, and then proceed to gauge the symmetry acting on the second and third layers, and then third and fourth layers, and so on. And the claim is that after you do all of this, these layers become coupled together, and you get a k plus one dimensional Hamiltonian. Of course, this k plus one dimensional Hamiltonian will of course depends on your initial k dimensional Hamiltonian for each layer. And our proposal is that if you choose the initial k dimensional Hamiltonians to spontaneously break the symmetry A completely, then the k plus one dimensional Hamiltonian you get at the end will be the topological order corresponding to this symmetry, corresponding to this k dimensional symmetry. Okay.
Otherwise,
otherwise it will be, for example, if the k dimensional Hamiltonian is disordered, there's no symmetry breaking, you'll get something completely trivial. And if we partially break symmetry A, you probably get something in between. Probably it is a topological order corresponding to a smaller symmetry.
Uh-huh.
Yeah, that's uh this claim is conjectural. It's tested by examples, but I don't have a general proof. Okay. So this is a general prescription for this simplest situation for this simplest type of symmetry. Um, I forgot to say, although I assume the symmetry to be invertible, abelian on site, the symmetry can be higher form, can be a subsystem symmetry, as you will see by examples. Okay. But let me first start from a very simple example. That is the construction of the 2D toric code from 1D Z2 symmetry. According to the prescription in the previous slide, what we want to do is to we take many copies of a 1D system and stack them into a 2D lattice. And then for the moment, let's choose the Hamiltonian for each 1D system to be the 1D transverse field Ising model. So the initial Hamiltonian take this form. Here n is the layer index and j is the side index within each layer. As you can see, this Hamiltonian describes 1D Ising model, decoupled 1D Ising model acting on each layer. Okay, and j and h are coupling constants. So this Hamiltonian has a Z2 symmetry acting on each layer, and the symmetry generator for each layer is given by U sub n, which is the product of x acting on all sides on that layer. Okay. And according to the prescription just described, our goal is to sequentially gauge the diagonal Z2 symmetry generated by Un times Un plus 1. It actually should be Un plus 1 inverse, but since we are considering Z2 symmetry, there's no difference. Okay, so since I do not assume that everyone are familiar with gauging on the lattice, so let me first spend a little time to recap how gauging works on the lattice using the single layer Ising model. Recall that we ultimately want to gauge the bilayer Z2 symmetry, but at this moment, as a review of gauging, let me use a single layer transverse field Ising model. So the Hamiltonian of this model is just this minus dz minus there's a dz term, also x term lives on this type of 1D lattice. And the first and the Z2 symmetry is just a product of x over all sites. The first step of the gauging is that we introduce gauge field sites, namely these black sites, in between the original macrofield sites. And then we demand a local Z2 symmetry generated by these operators, S sub I. So this operator acts on these three sites. It has a poly X acting on one matter field site and two poly X acting on the two neighboring gauge field sites. It's the analog of the Gauss's law operator in the U1 gauge theory or in electromagnetism. Okay. So we want to demand this local symmetry, and but this Hamiltonian does not commute with this symmetry generator, so we need to modify the Hamiltonian. The single X term, the transverse field term, is already symmetric, so we don't need to do anything to this term. But the ZZ term is non-symmetric, and the minimal way of modifying this term to make it symmetric is to just add another poly Z acting on the gauge field site between the original two matter field sites. So after this is called minimal coupling, and after this modification, we obtain a new Hamiltonian H prime, which is a Hamiltonian after gauging, and this Hamiltonian enjoys these local symmetry S sub I for every I. Okay. And as the last step of gauging, we wanna restrict our Hilbert space to the so-called gauge invariant subspace, which is a subspace where this Si, these local Z2 symmetry generators are trivial, namely Si equals to 1. And this is nothing but the analog of the Gauss's law in electromagnetism. Okay. Yeah, and this X is like the charge, and these two X are like the electric field. One particular consequence of imposing this Gauss's law is that let's assume periodic boundary condition, then imposing this Gauss's law implies that the original global G2 symmetry has been enforced in the Hilbert space. And this is because the original G2 symmetry, which is the product of all x, is equal to the product of all the Si. And if you require Si equals to 1, then the original G2 symmetry is also trivial. Okay. Any questions so far? Okay. So this is a recap of lattice gauging, and now let's come back to our later gauging problem. So recall we have this kind of 2D lattice, and we want to sequentially gauge the bilayer diagonal G2 symmetry on this lattice. So let me start from the first and second layer. We will treat each round of qubits, namely each two qubits with the same J index, as a single unit cell, and then regard this bilayer system as a quasi-1D system. So as a first step of gauging, we will introduce gauge field sites between each pair of unit cells. And then we demand this type of local symmetry. This is analog of the Gauss's law operator in the previous slide. The difference is that here, the matter field part has two qubits because each unit cell now has each unit cell now has two sites. Okay. So this is the local symmetry operator, and in order to commute with this local symmetry generator, we need to modify our Hamiltonian. Again, the single x term in the Hamiltonian is already symmetric. It don't need to do anything to it, but the GG term in the original Ising Hamiltonian need to be modified, and this is what need to do. This is the minimal way of coupling these GG terms to the gauge field term. It's just very similar to what we did in the previous slide. Okay. And then after projecting to the gauge invariant subspace, we finish gauging for the first two layers. And next, we need to proceed to the second and third layers and gauge the bilayer C2 symmetry acting on these two layers. And again, we will impose a local symmetry like this, just shift the layer index by 1. And then again, we need to modify the Hamiltonian terms. So this term is already symmetric with the local G2 symmetry in the second and third layers. So we don't need to modify this, but this term needs to be further modified. It becomes a term like this. And then we also need to modify the GG term acting on the third layer to this form. Is this clear so far? Okay. So we can proceed and gauge the gauge the diagonal G2 symmetry on the third and fourth layers and so on. And eventually we get a bulk lattice of this form. You can also see the pattern of the Hamiltonian, and eventually we get a Hamiltonian of this form. This is a Hamiltonian in the bulk away from the boundary. We still have the single x term, which originates from the transverse field term in the original Ising model, and is not modified because it's always symmetric with it commutes with all the local symmetry generators. And this term is a modified Ising term, so that this 2z comes from the original Ising GZ couplings, and these two black z's are the gauge field coupled during the gauge field algorithm introduced during this layered gauging procedure, as you can see from this term. Okay, and this whole Hamiltonian and the Hilbert space is subject to this type of Gauss's law constraint. And now you can see that if we set H to be 0, that corresponds to the original Ising model being in the ferromagnetic phase. And then this bulk Hamiltonian, together with this Gauss's law constraints, realizes the well-known toric code topological order. And if you want, since this model is the toric code model is frustration free, if you want, you can also soften this Gauss's law by adding it as a stabilizer into the Hamiltonian, and that recovers the standard toric code Hamiltonian. Okay, and this is the elementary example about how to generate two tutorial codes from 1EZ2 symmetry. Any question about this example?
From this example, can I see why in general if the k-dimensional system breaks the symmetry completely, then the k+1 dimensional system should be that particular topological order?
Um, I have a uh, I have a very non-rigorous argument that convinced myself, but it doesn't serve as a proof. So basically, so when we do this type of layered gauging, when we do this type of layered gauging, I'm thinking that we are gradually growing the topological order. And so if you take this picture, I can regard the original 1D system, original k-dimensional system as an ultra thin layer of topological order, and that topological order need to have some ground state degeneracy. You need to have some ground state degeneracy if you have periodic boundary condition, and that degeneracy comes from the spontaneous symmetry breaking. This is my picture. It doesn't serve as a rigorous proof, but that's all my intuition. I don't have a better way of showing this actually.
I see. Thanks.
Yeah. Yeah. It's more like an empirical result from the examples I tried. Okay, so let's try to understand what happened in the previous example. We try. I want to build some intuition about why we generate some bulk model that enforces the symmetry on the boundary. And yeah. So what we did is as follows. So in the first step, as in the previous prescription, we gauge the symmetry U1 alpha times U2 alpha inverse. And as I said previously, when you gauge the symmetry is also after gauging the symmetry is enforced in the Hilbert space, and this is at least true for the case of abelian symmetry. And this is the first step. And secondly, when you proceed to gauge U2 alpha times U3 alpha inverse, this symmetry is also enforced. And eventually, you enforce the symmetry UN alpha times UN plus 1 alpha inverse. You require this generator equal to 1 for all n. And a particular consequence is that if you multiply all of these generators together, you find that U1 alpha times U capital N alpha inverse equals to 1, where this capital N is the total number of layers. Suppose you take open boundary condition in the layering direction. Okay. And then this is nothing, this just means that the symmetry A that you start with has been enforced on the boundary of the k plus 1 dimensional system. Because when you take periodic boundary condition in the intra-layer direction, but take open boundary condition in the layering direction, then your boundary is basically the first layer and the capital nth layer, and this is the symmetry acting on the boundary. These generate symmetry A acting on the boundary, and they equal to 1. It means that the symmetry is enforced. Okay. And as I mentioned previously, this type of this phenomenon of enforcing a symmetry is the basic intuition behind topological holography. Wait a minute, I saw a question in the chat. Oh, the question in the chat is asking about how to determine the lattice geometry of the gauge field. So basically, at least for the case of zero form symmetry, given any lattice, the standard rule is to introduce gauge field in the links between matter field sites. And there are apparently different ways of drawing the links. I mean, given some sites that form a lattice, there are different ways of drawing the links, and different ways of drawing the links give you different ways of introducing gauge fields. But my conjecture is that these different ways of gauging give you equivalent topological orders. I tested this in some examples, but again, I don't have a rigorous proof. Okay. So back to this explanation. As I said, when you do this type of layer gauging, you enforce a symmetry on the boundary, and this is roughly speaking the intuition behind topological holography. So to see this precisely, more precisely, let's imagine we have some 2D topological order defined on a disk, and let's assume there's no excitation in the bulk, no anyon excitation in the bulk. Then the only possible dynamical physical degree of freedom live on the boundary of the disk, and that defines a one-dimensional effective boundary theory. And then because there's no anyon excitation in the bulk, actually you can freely generate an anyon loop in the bulk. What that means is that this anyon loop operator equals to a positive constant when acting on this state with no anyon excitation. But then if you push this anyon loop to the boundary, some of the anyon loop will actually become a global symmetry acting on the boundary. And such global symmetry equals to the global symmetry generator equals to a positive constant. This means that the symmetry has been enforced on the boundary. Okay. This is roughly speaking the intuition behind topological holography. Although there's many subtleties in this type of argument, which I'll not go into. Okay. So this is the first and most elementary example. And next, let's try to consider a slightly more interesting example, that of subsystem symmetry. As I advertised at the beginning, this new method can be used to deal with subsystem symmetry and fractal topological order. So let me show it by this example. So now we are consider now we have k equals to 2. We consider a 2 plus 1D model to start with. So our single layer Hamiltonian is given by this 2D plaquette Ising model. It is defined on a 2D square lattice with qubits living on the sides of the 2D square lattice. And the Hamiltonian takes this form. It's just a product of 4Z around each plaquette. If you want, you can also add a transverse field term, but for our purpose of constructing bulk topological orders, it suffices to just consider this Ising term. Okay. This Hamiltonian, the single layer Hamiltonian, has a subsystem symmetry. Namely, it commutes with the product of X over any single column and any single row. So these are the symmetry generators. This symmetry acts on rigid subsystems, so they are called subsystem symmetries. So according to our previous prescription, what we wanted to do is to again stack these single layer models into a 3D lattice and then sequentially gauge the bilayer subsystem symmetry, the subsystem symmetry acting on each pair of layers, 1, 2, 2, and 3, and so on. Okay. But there's an interesting feature in the case of subsystem symmetry. So at least in this example, there are at least 2 different ways of gauging the subsystem symmetry, and they lead to different bulk topological orders. And let me explain them one by one. So the first obvious way of gauging the subsystem symmetry is to regard it as a collection of 1D symmetry and then sequentially gauge these 1D symmetry. Recall that the symmetry is the product of X acting on each single column and each single row. So these are all 1D subsystems. And we know how to gauge 1D digital symmetries. So you can imagine sequentially do this gauging. So you first gauge the symmetry acting on the first row and the second row and third row. After going through all the rows, you do the gauging for the first column and the second column and so on. So if you do this kind of sequential gauging, sorry, there are 2 layers of sequential gauging here. First you need to do this gauging for each column and row, and then you need to move on to next pair of layers and so on. And after you do all of this, I will skip the details. The bulk model obtained is as follows. Here I have added the Gauss's law term as stabilizer into the Hamiltonian. So these are originally Gauss's law terms, and I softened them by adding them to the Hamiltonian with a positive coefficient. As you see, I'm showing this. I'm writing this bulk Hamiltonian, which is a 3D Hamiltonian on the 3D cubic lattice, with qubits living on the links. And these vertical links, the links in the z direction, or originally they come from the matter field in the original 2D plaquetizing model. And these horizontal links in the xy plane are basically gauge field. They are gauge field degree of freedom introduced during this gauging procedure. And this Hamiltonian actually realizes the well-known the famous x cube fractal topological order. First introduced in this paper. I need to say that in the original x cube fractal in the original x cube model, there's actually another stabilizer, which is the 4x term in the xy plane. But that term is not an independent stabilizer. It is equal to the product of these two, and therefore we don't have that term in our Hamiltonian. But this, because it is not independent, that doesn't change the ground state and doesn't change the topological order. Okay. Any question about this? Okay. So this is the first way of gauging this subsystem symmetry, and there's actually a second way of gauging. Since this is not so obvious, let me again explain this gauging in the case of a single layer model. So recall that our single layer model consists of 4 z terms acting on the 4 qubits around each plaquette. In the second way of gauging, instead of introducing gauge fields in the links, we introduce gauge field size at the centers of each plaquette, and we demand this type of local symmetries. We can regard this as a gauging of the subsystem symmetry because if you take the product of these local symmetry generators along any column or any row, you can recover a generator of the original global symmetry. Okay. So in the end of this gauging, the original subsystem symmetry will be enforced. Okay. And then after defining this local symmetry, we need to modify the Hamiltonian term in order to commute with this symmetry. And the minimum way of doing it is actually very simple. We just add another z at the plaquette center for each full z term, and you can check that this operator commutes with this local symmetry. Okay.
Can you remind me which one is matter, which one is gauge field?
The white one is matter. Black one is gauge field.
Mm-hmm.
Yeah. Our original Hamiltonian is like this, and we introduce gauge field. We introduce one gauge field set for each plaquette center, and we require this type of Gauss's law. So it's 1 matter and 4 gauge field.
Then in the previous way of gauging, you are also you said there are two.
Yeah.
You said there are two
yeah.
Sequential gauging procedures. One is within the layer and the other is between the layer.
Yes.
But why do you want to have a gauging procedure within the layer?
Because I want to gauge the symmetry generated by all of these generators. But these are like this. There are many. They can be decomposed into many 1D symmetries. I need to sequentially gauge all of these 1D symmetry. So I mean, for example, this is a symmetry. These are the symmetries acting on each single column, and these are the symmetry acting on each single row. If I want to gauge the symmetry, which means I need to gauge all of these 1D symmetries. So I need to, for example, start from the first row, gauge the 1D symmetry acting on the first row, and then do the gauging for the second row and the third row. After you go through all the rows, and you need to do the gauging for the first column and the second column and third column.
But each time you gauge the product symmetry between the two layers.
Yes.
Okay.
Yes. Yeah. Maybe I should have shown more details for the first way of gauging. Yeah, but that's basically what he does.
I have a related question.
Uh-huh.
So in the two ways of gauging, do you end up gauging the same symmetry or not?
I'm guessing that somewhat different because in the first way of gauging, so this symmetry has a subgroup which is a product of X over all sites.
Yes.
That symmetry seems gauged twice in the first way of gauging.
Uh-huh. So it might be that it was not the diagonal one was not gauged in the end because you.
Yeah. But I also don't know how to modify the first way of gauging. For example, you can, if you skip the last row, then you didn't
Yes.
you avoid like repeated gauging, but that doesn't seem to modify the Hamiltonian. Doesn't seem to modify the bulk Hamiltonian. So I don't know what happens.
Mhm, mhm.
Yeah,
But yeah, I think I agree that you didn't gauge
yeah.
the global one somehow for the first
Yeah. Actually, if you do this two different way of gauging to this singular Hamiltonian, the obtained lattice two lattice models are related by the two lattice models obtained are related by a global Z2 gauging. So that's probably
Uh-huh.
maybe it's the same thing. Yeah.
So in the second one you would get a trivial, but in the first one for single layer.
For single layer, in the second one, you get the trivial. It's basically the
Trivial.
self-dual of the
Uh-huh.
transverse field plotting model.
Uh-huh. But for the first one you get torical or something?
Um, you get torical perturbed by using this Hamiltonian, you get torical.
Mm.
Yeah. And if you have transverse field term, you get a perturbation. Okay. Yes. So let's get back to this second way of gauging. If you what I explained here is for the single layer model. But if you now do the similar thing for bilayer system and do this sequentially for all pairs of layers, all nearest neighbor pairs of layers, you get a bulk model like this. It's a 3D model, and again, I have added the Gaussian law term into the Hamiltonian as a stabilizer. So the lattice is this 3D lattice is different from the previous one. It is the alternating stack of the white and black lattices. They are both square lattices with qubits living on the sides on the vertices of the square lattice, but they are relatively shifted by half lattice constant in both x and y direction. So the vertex of the black lattice sides, the vertex of the black lattice corresponds to the Plaquet center of the white lattice. Okay, and the two types of stabilizers are given by this and this. You can actually see the analogy with the single layer gauging. So if you look at this stabilizer from the d direction, it looks like this. And if you look at this stabilizer from the d direction, it just looks like this. And this is a different fractal model. Different from the X cube model in the previous slide. And this model is actually an anisotropic fractal model, first described in this paper, and and also constructed by a few other different methods in the other papers. This model is anisotropic, meaning that it looks like fractal in the XY direction, but looks like ordinary topological order in the Z direction. So the excitation in this model are free to move in the Z direction, but has restricted mobility in the XY plane. And the ground state degeneracy also only depends on the system size in the X and Y direction.
These two terms don't commute, right?
They commute. For example, this X anti-commutes with this D, but this X anti-commutes with this D,
Oh,
so they commute.
I
Yeah,
see.
they are just shifted. They're not acting on the same layer. If you look at the black and white, they are centered on different layers. Okay.
So, Sean, so these models have some kind of self-duality.
You mean this Spock model?
Yeah.
Let's see.
Is it reflected in the excitations? So if I
How
do
did you
a
see
Does
half
the?
have an
lattice,
EM duality, like a
ah,
half shift, like in the torical.
yeah, if I do
Uh-huh.
a half lattice translation together with some internal operation that exchanges x and z,
Yeah,
that's the symmetry of the
Okay, okay.
Hamiltonian.
yeah.
Yeah.
And I was asking whether this translates into some relation between the excitations.
Yeah,
Whether
then it must be, I think so. Yeah, I think so. Yeah.
then if I drive a confinement transition of this flucton topological phase, is
Uh-huh.
there anything interesting happening at the transition?
I don't know. I'm not sure whether anyone has studied this before. Yeah, that's an interesting question. You're saying confining in the self-dual line, right?
Yeah.
Uh-huh. I'm not sure about this. Yeah,
Thanks.
yeah, that's an interesting question. Mhm. Yeah. Okay. Let me proceed. So the last example that I want to discuss in this talk is okay, I don't have much time. Yeah, the last example is example with anomaly. So it's an example with a 1D anomalous T2 symmetry. So the single layer Hamiltonian will again be this very simple Ising Hamiltonian. Yeah, in the ferromagnetic phase. But now I will consider a different T2 symmetry. That is this anomalous T2 symmetry first introduced in this paper. So the symmetry generator is part of all X, but addressed by a sign factor plus minus one. This factor is basically assigning a factor for I to every domain wall. But assume periodic boundary conditions, there are even number of domain walls. So this is ultimately a sign factor. And this symmetry is turns out to be anomalous T2 symmetry. There's no way to gauge it, to gauge this single layer symmetry. But in our prescription, what we want you to do is to gauge the bilayer symmetry generated by UN times UN plus one minus UN plus one inverse. And this symmetry is anomaly free. And in principle, you can do it. Okay, yeah. Although this gating is possible, having a non-on-site symmetry still give you introduce some complexity, and actually the procedure becomes somewhat different from the previous simplest situation where you have on-site symmetry. So let me describe this more carefully. So as a first step, we gauge the diagonal symmetry on the first two layers, U1 times U2 inverse, and yeah, you can add an inverse, but there's no difference because it's T2 symmetry. So we first gauge U1 times U2, but if after this gauging, we immediately found that the U2 symmetry, the U2 symmetry generator, does not commute with the Gauss's law obtained from this type of gauging, obtained from this step of gauging. So U2 is no longer a valid symmetry after this first step of gauging. But in the second step, we wanted to proceed to gauge U2 times U3 inverse. And if U2 is not a valid symmetry, there's no way of doing that. So the resolution is also somewhat straightforward. We just couple the symmetry, the original symmetry U2 to the gauge field, so that it commutes with the Gauss's law. Just like what we did for the Hamiltonian term. The Hamiltonian terms that does not commute with the Gauss's law, so we need to couple them to the gauge field. And we can do the same thing to this symmetry generator and obtain a new symmetry U2 prime. Although there's actually some subtlety here, because U2 is a non-local operator, there isn't a unique way of coupling U2 to the gauge field in order to commute with the Gauss's law. But at least in this example, I think I checked that there are two different ways of doing this, and they lead to equivalent bulk topological order. So we'll just choose one way of doing that, and obtain a new symmetry U2 prime, commutes with both the Gauss's law and the Hamiltonian. And then we can proceed to gauge U2 prime times U3 inverse, and then modify U3 to U3 prime, and then proceed to gauge U3 prime times U4. And repeat these steps until we get a bulk lattice model. Okay. I will skip the detail of this calculation. The calculation is actually very complicated. Half of my time spent on this project is to work on this example. And the bulk lattice thus obtained takes the same form as the previous toric example. It's just this lattice. But the bulk stabilizers look a little complicated. So there are two types of stabilizers. This one is simpler. It's just a full Z term, also showing it also exists in the toric example. But this one it's a new stabilizer. This is product of 4x times some other diagonal operators. So in this picture, this S is a square root of Z, the S gate, and each blue bond represents the control Z gate. And the X operator do not commute with these diagonal operators. So my convention is that when I draw this picture, my convention is that the X operators are multiplied on the left, and all the other diagonal operators are multiplied on the right. Okay, and then and this is these two are the bulk stabilizer. You can show that they commute, and the Hamiltonian is frustration free on the torus and has fourfold ground state degeneracy. Okay. Yeah, and since one can show that this model is frustration free, we can actually use this stabilizer to simplify the other one. Namely, if you assume in the ground state subspace, since this stabilizer is equal to 1, you can use this as a relation to simplify this operator, and the result is as follows. So in other words, you can describe the ground state of this model either by the stabilizers in A and B or the stabilizers in B and C. Okay. And furthermore, I can show that this model actually realizes the double semion topological order first introduced in this paper. The way to show it is the key to show this is to find the loop operator that can generate to find the string operator generating semion and then check the semion statistics. The way to do it is actually to let's say we take this stabilizer, take the product of this type of stabilizers in a rectangular region, and then this results into a loop operator, which is presumed to be the semion loop, and then you can check that the horizontal arm and the vertical arm of this loop operator anti-commutes with each other, which is the signature of semion statistics. Okay. Any question about this example?
Yes, I have a question. So you said that after the naive gauging and introduce the Gauss law, the U2 will not commute with Gauss law, and you need to introduce the U2 prime. I'm wondering if this is a necessary consequence of the anomaly.
Necessary consequence of the anomaly. It sounds closely related because the reason that U2 is no longer a valid symmetry is just because U2 is not an on-site symmetry. So when you do the gauging, you change your basis so that the U1 times U2 become an on-site symmetry. But then U2 in this basis is not an on-site symmetry. And in general, we have a non-on-site symmetry. It doesn't.
I see.
I guess it doesn't commute with the local symmetry generator. This is this argument. I didn't prove it's necessary, but this sounds. So it sounds like this will generically happen when you deal with anomalous symmetry.
I see. Thank you.
Yeah.
But
Mhm.
the argument just not only uses the non-uncertainties, not the anomaly.
That's right. Yeah.
It might be possible that we first deform the anomalous symmetry in some way, then maybe after gauging the U1, U2 inverse, the U2 is still a valid symmetry, right?
Uh, uh, what do you mean by deform the symmetry? Is there any degree of freedom that you can change in the
Like
symmetry?
conjugating the symmetry by more complicated circuit.
Oh, okay. By some finite circuit. And
Yeah.
uh-huh. Hmm.
I feel that's in spirit, that's very similar to what you are doing. You are adding some more degrees of freedom.
Yes. You definitely cannot find any basis so that the symmetry becomes on-site, right? Yeah, but maybe you can design some clever non-on-site anomalous symmetry which still respect the local Gauss's law. Yeah, that might be possible.
Mhm.
Yeah, yeah, yeah. I'm not sure how to do that, but it might be possible.
Mm.
Yeah. Okay. Okay. If no other question, let me come back to this. So this is the example of the double semi-on topological order. Yeah, there are some other square lattice double semi-on topological order models in the literature, and our model is similar to one of them, but still I didn't find a easy way to relate these. I mean, I didn't find a simple unitary transformation that can map my model to the other ones. So might be, yeah, I'm basically saying and this might be a new square lattice double semi-on model. Okay. So so in the paper I have a few other examples. For example, in particular, I have one example for non-abelian symmetry, which is a 1D discrete group symmetry G, zero form discrete group symmetry G, and also the 1D Repli symmetry, which is a non-invertible symmetry. And also have a one-form symmetry example. But given the time constraint, I will not talk about these examples in this talk. Okay. Now, near the end of this talk, let me quickly mention some other related papers. So, as I said, in this work, we developed a method that can generate k plus one dimensional lattice topological order from k-dimensional lattice symmetry. But this is not the first method that can do this type of thing. In an earlier paper, my collaborator Wenjie and me has another construction, which is a somewhat ad hoc method to write down k plus one dimensional stabilizer Hamiltonians, topological stabilizer models, using some what we call k-dimensional generalized Kramers one-year dualities. Yeah, there's always some generalized symmetries when you talk about Kramers one-year dualities, and these are basically the symmetry corresponding to the k plus one dimensional topological order. The advantage of that construction is that it is mathematically rigorous, so we can rigorously prove that we have constructed a non-trivial topological order, and we can rigorously describe the boundary theory of that topological order. It's more rigorous than the paper that I'm talking about today. But because we want mathematically rigorous, we only work out we only consider on-site D2 symmetry to some power. Although the symmetry can be higher form symmetry, can be subsystem symmetry, they are all on-site D2 symmetries. Okay, and later there's also another construction called iterative gauging. they're basically doing the following thing. So you start from some 1D model with some symmetry, you gauge the symmetry and obtain this will generate some matter field, some gauge field sites, and you regard this gauge field as a second layer, and gauge the dual symmetry acting on that second layer to generate the third layer, and then gauge the dual symmetry acting on the third layer to generate the fourth layer. If you do this, you can generate a bulk, a k plus one dimensional model from a k dimensional symmetry. But this method is intrinsically incompatible with anomaly because if you have anomalous symmetry, you just cannot do the first step. And our work today, the work I talk about today, can be regarded as a generalization of these two previous methods. Yeah. Also, I need to
Sorry,
mention that.
Sean. In the second approach, the dual symmetry is usually with a different form as the original symmetry, right?
Right.
Then,
For example, if you start from symmetry G, you first gauge symmetry G, and then gauge rep G, and then gauge G, and then gauge rep G.
then one has to do exactly an even number of times? Or
I guess doesn't matter. I mean, you generate a. You first you have matter fields on your first layer, and you gauge to get gauge fields as your second layer, and then the dual symmetry only acts on the second layer. Yeah, then you gauge that second layer symmetry to obtain the third layer, and then you do this repeatedly. You generate a bulk model. I guess even or odd doesn't really matter. I mean,
okay.
whether you do it even or odd time only determines your last what your last layer is.
Mm-hmm.
Yeah.
Okay.
Yeah. Okay. Also, I want to mention a paper posted earlier than our one, the one by Nat. So in this paper, they introduce a gauging perspective of the hypergraph product codes in the quantum error correction code, and also I guess also a perspective of balanced products. I'm saying this because our method, our construction actually can also be regarded as some sort of generalization of hypergraph product in quantum error correcting codes. So if you regard the k-dimensional lattice system, recall that we have some k-dimensional symmetry breaking system, and that can be regarded as a generalization of some classical error correcting code. And the layered gauging procedure is basically taking the product of this k-dimensional code with the repetition code, with the 1D repetition code. And this connection is made more precise in this paper. Yeah, and I think NAT also has the same set of orders also have a generalization of this construction beyond the conventional product constructions. And this paper is just posted a few days ago. Okay. So let me summarize. So in this talk, I introduced the so-called layer gauging method, which is a method to generate k plus one dimensional topological order from k-dimensional lattice symmetry. So I have successfully implemented this method in a number of examples with different type of symmetries. That's why I conjecture it's a very general method. But unfortunately, I don't have a rigorous proof of its generality, and this is something that should be tried to do in the future. And also, from this method, I have produced a new square lattice double Sebian model, but all the other examples are actually are basically already known examples. So another interesting question to explore in the future is whether this method can be used to generate other new interesting topological lattice models. Okay, and also related to what I said in the previous slide, since this method can be regarded as some generalization of product constructions in the error correcting code, so maybe one can consider whether this can be used to produce some interesting quantum error correcting codes beyond the CSS type. I think NAT is already working in this direction, following their developments. Okay. And thank you for your attention, and please ask other questions if you want.
Okay, thank you, Sean, for the very interesting talk. Any further questions? Sean, I have a question. Just uh, let me just ask this. What's the significance of having a new square lattice double semi-model?
Not very significant. Yeah. Yeah, it just shows that this that's trying to say that this method may be possible uh, to to uh, to produce new lattice models that we don't know before. But whether the lattice model is useful, it depends. The double seminar model is probably not very useful compared to the existing ones. But maybe in the future I can find some other interesting models. Yeah,
Mhm.
yeah.
Yes, I have a question.
Mhm.
So I'm wondering, in your general construction, you used U1, U2 inverse. Uh,
Yes.
why is there an inverse? Why don't you choose U1, U2?
Um, you can choose U1, U2. For the billing case, actually, there's no much difference. Um, there's actually as I mentioned briefly, there's a generalization of the construction to the case of non-abelian group. And in that case, whether you have an inverse or not does matter. So I'm writing U1 times U2 inverse just to match with my convention in that case, actually. Yeah. In the billing case, I think there isn't there isn't much. I think it doesn't matter
So
because U and U inverse generate the same symmetry.
oh, I see.
I mean, they satisfy the same multiplication rule because it's abelian.
Okay, I see.
Yeah.
And then one more question. So how important is translation symmetry in this general picture?
Um, I suppose is you mean whether what if the lattice model is not translation invariant, right?
Yes.
I suppose it doesn't matter.
Okay. Thank
Yeah.
you.
I mean, again, I don't have a proof, but I mean, for example, if you adjust, I mean, let's say in the Torah code example, at least you can make the coefficient of the ZZ coupling to be site dependent, and that doesn't change the bulk total order. Um, yeah. But I
Thank
don't
you.
have a general proof. Yeah.
Thank you very much.
Yeah. Thanks.
So regarding this U2 inverse, if the symmetry is non-invertible, what does it mean?
If the symmetry is non-invertible, you actually need each layer to have both the left symmetry and the right symmetry. And then what you need to gauge is like the left symmetry on the first layer times the right symmetry on the second layer. Yeah, something like that.
Okay.
It's less elegant than a Boolean case. Yeah.
Mhm.
Yeah.
Okay, any
Um.
other questions?
Mhm.
Yeah, so I have a don't know if it's a very well formulated question. So here I think your work is trying to do this lattice to lattice gauging process. And at the beginning you mentioned that there are already some work doing this thing
Yes.
IR theory to IR theory gauging, like just field theory level.
Yeah. But they have both field theory construction and lattice model construction.
Yeah, so
Yeah.
here I mean so there seems possibly to be some like embedding or correspondence between this lattice gauging and this field theory level gauging. Is that true? Like your for
Um.
example, more concretely,
mm,
like the gauge field you introduced should somehow be related to the IR theory gauging. Is that true?
um. I don't know how to formulate these construction in terms of gauging. Um. They just have some. They basically just have some mathematical description of the symmetry, like a category, and then they have a rule of writing down the lattice model in the higher dimension. I don't know if they have any. I don't know any way of interpreting this construction as gauging. So I
I
didn't
see.
see a direct relation to the construction I presented here actually.
I just want to say because there seems to be two parallel lines and the correspondence between the microscopic the boundary part is IR versus some lattice, and the bulk part is also IR versus some lattice. Seems to be some interesting connection in, yeah, I don't know.
Maybe I still didn't quite understand your question.
Okay, I probably it's not very well formulated, but let me just ask one point. Probably you know the answer. So I think the gauge field you introduced in the lattice Hamiltonian and gauge it from the IR perspective, is it like um is it just the ordinary gauge field we use like in electrodynamics or something? Yeah, the standard fiber bundle or principal bundle.
It is, but it is the gauge field for the k-dimensional layer. So you have is a k plus 1 dimensional bulk model, but the gauge fields are introduced as k-dimensional gauging. So it's different from the. You can also regard the k plus 1 dimensional topological order as a gauge theory, but these gauge field degree of freedom are not gauge field in that sense. It's gauge field for the k-dimensional layers. Yeah.
Oh, I see.
Yeah.
That's this difference.
Yeah, that's the difference.
I see. Okay, thank you. Yeah, I got it.
Okay, any other questions?
I have a question about the generalization of this formalism. Is this possible to generalize this to the fermionic case?
To the what?
Fermionic case.
I'm not sure. I didn't try an example.
Oh, okay.
Yeah.
Thank you.
Yeah, thanks.
Other questions? Okay, Sean, as our familiar background is reminding us, we always have to wait for 7 seconds to see if people have other questions. I have waited for 7 seconds. There isn't. Yeah, thank you very much for the very interesting talk. Thank you.
Thanks.
Bye.